Integration using trigonometric identities and standard integral forms. A complete visual guide from Unit 8 Integral Calculus for Class 11, 12, and JEE aspirants. Here are the 10 standard integral forms you must master. These appear repeatedly in JEE, board exams, and competitive tests. Each involves expressions with x squared plus a squared minus x squared, or quadratic expressions ax squared plus bx plus c. Let us go through each one systematically. The key idea behind these standard forms is trigonometric substitution. When you see a squared minus x squared under a square root, substitute x equals a sin theta. For x squared plus a squared, use x equals a tan theta. And for x squared minus a squared, use x equals a secant theta. Think of a right triangle where theta connects x, a, and the square root expression. Form 1, the integral of dx over x squared plus a squared. We substitute x equals a tan theta, so dx equals a secant squared theta d theta. The denominator becomes a squared times tan squared theta plus 1, which is a squared secant squared theta. The secant squared terms cancel, leaving 1 over a times the integral of d theta, which gives theta over a. Since x equals a tan theta, theta equals arctan x over a. The final result is 1 over a times arctan of x over a plus c. Form 2, the integral of dx over the square root of a squared minus x squared. Here, substitute x equals a sin theta. Then dx equals a cosine theta d theta. The square root simplifies to a cosine theta using the identity 1 minus sine squared theta equals cosine squared theta. Everything cancels beautifully, leaving just the integral of d theta, which is theta plus c. Since x equals a sin theta, theta equals arcsine of x over a. Form 3, the integral of dx over the square root of x squared plus a squared. Substituting x equals a tan theta, the square root becomes a secant theta. We get the integral of secant theta d theta, which is the natural log of secant theta plus tan theta. Substituting back, secant theta is the square root of x squared plus a squared over a, and tan theta is x over a. After simplification, the result is log of x plus the square root of x squared plus a squared plus c. A similar result holds for x squared minus a squared. Form 4, the integral of dx over a squared minus x squared. This one uses partial fractions, not trig substitution. Factor the denominator as a minus x times a plus x, decompose into partial fractions, 1 over 2 times the quantity 1 over a plus x plus 1 over a minus x, integrating each term gives logarithms. The final result is 1 over 2 times log of the absolute value of a plus x over a minus x plus c. For x squared minus a squared, the result is similar with x minus a over x plus a. What about integrals with ax squared plus bx plus c in the denominator? The trick is completing the square. We rewrite ax squared plus bx plus c by factoring out a and completing the square inside. This gives us a perfect square plus or minus a constant, which is exactly form 1 or form 4. For example, the integral of dx over x squared plus 4x plus 13. Complete the square, x squared plus 4x plus 4 plus 9, which is x plus 2 quantity squared plus 9. Now use form 1 with t equals x plus 2 and a equals 3. The answer is 1/3 arctan of x plus 2 over 3 plus c. Now, what if the numerator is px plus q instead of just a constant? The key idea is to split the numerator. Write px plus q as a times the derivative of the denominator plus b. The derivative of ax squared plus bx plus c is to ax plus b. So px plus q equals a times to ax plus b. Compare coefficients to find a and b. This splits the integral into two parts. The first part has the derivative in the numerator, which gives a logarithm. The second part is a constant over the quadratic, which is our standard form 1 or form 4 after completing the square. The same technique works when there is a square root in the denominator. The square root forms are some of the most important results. First, the integral of the square root of a squared minus x squared equals x over 2 times the square root plus a squared over 2 times arcsine of x over a plus c. This is derived using the substitution x equals a sin theta. Notice that geometrically, this represents the area under a semicircle. The integral from minus a to a gives pi a squared over 2, which is the area of a semicircle. Similarly, for x squared plus a squared and x squared minus a squared, the formulas involve the square root multiplied by x over 2 plus or minus a logarithmic term. Let's work through an example. Evaluate the integral of 3x plus 5 over x squared plus 4x plus 13 dx. Step 1. Split the numerator. The derivative of x squared plus 4x plus 13 is to x plus 4. Write 3x plus 5 as a times 2x plus 4 plus b, comparing coefficients, 2a equals 3, so a equals 3 halves. And 4a plus b equals 5, giving b equals minus 1. Step 2. The integral splits into 3 halves times the integral of 2x plus 4 over the quadratic, which gives a logarithm, minus the integral of dx over the quadratic. Complete the square, x plus 2 quantity squared plus 9. Step 3. Apply form 1 with t equals x plus 2 and a equals 3. The final answer is 3 halves log of x squared plus 4x plus 13, minus 1/3 arctan of x plus 2 over 3, plus c. Here are 5 exam tips for integration. First, always complete the square for quadratic denominator forms. Second, for px plus q numerator, split using the derivative of the denominator. Third, memorize all 4 basic standard forms, they appear in every JEE paper. Fourth, for square root forms, remember the trigonometric substitution and the formula pattern. Fifth, watch the sign carefully, a squared minus x squared gives a different result than x squared minus a squared. Keep this quick reference card handy. If you found this helpful, like the video and subscribe to MAGPIEHUB for more JEE and board exam solutions. See you in the next one.